Now, within software, we have what we call Pareto analysis. I'm just going to hop quickly. And in the Pareto analysis, we can select and compare different system alternatives to your installation. So we have in blue here the reference. We modeled one alternative, which was the like-for-like replacement. Probably sounds very familiar to everyone because this is often applied when boilers are end of life. They do a like-for-like replacement, but we want to show in this case the building owner, he also was thinking about doing a like-for-like replacement, and we want to show him what a missed opportunity this would be. Hydraulic optimizations. We also analyzed the temperature regime reduction, where we know how the set points of the building, we know the load profile of the building. Everything is oversized, so we use that oversizing to basically lower the return temperatures, and we can actually analyze how low we could drive those. Integrated two solutions with heat pumps, and the last one, and this was just a question from our client: can we model one with a CHP? In the next step, let me change. We integrated energy prices, gas, electricity, carbon emission factors for gas and electricity, and these are just inputs. So the ones that you would be using or having, we just integrate those. In the next step, we integrate the different types of costs. So in terms of material costs, installation costs, so the cost of a pump and the cost of it being installed, and then additional study costs could be integrated in here if that is an additional cost. And what the software is doing now is basically comparing those different system alternatives against your current reference design or installation which is in place, and then we were able to see, because they all have year simulations being done, we can basically analyze and compare those different alternatives in terms of pump energy consumption, in terms of energy cost savings, and so on. So in the energy report, we have in yellow the reference. What was quite interesting to see, and we come across this in a lot of systems, is they had 5.2 megawatts on gas boiler capacity within the plant room in the existing situation. Now, they were planning to do that like-for-like replacement, so they were going to replace the old non-condensing boilers, those two, by the same size condensing boilers. Now, we also analyzed the actual gas consumption from, I think with this project, the last 5 years, and what we noticed is that a peak load during those 5 years was never more than a megawatt. So we actually asked the building owner, do you still want to install 5.2 megawatts? And we could reduce this to basically 1.1 megawatt, and we integrated in the heat pumps solutions over here 150 kilowatt air source heat pump, just to show actually what a small unit already can do in a system. All the data is for a year. So here we have the, for example, pump energy consumption. In the like-for-like replacement, they were going to replace the old pumps, which were 20 to 25 years old, by new pumps. And what we can actually see is, this is also what the pump manufacturer claims, a reduction of around 55% on pump energy consumption. But that's replacing them like for like. Now, when we look at the hydraulically optimized design and temperature regime reduction, we can achieve more than 90% on pump energy reduction for the same installation, knowing that in the existing situation they had around 20 pumps which were causing hydraulic problems. So those 20 pumps were eliminated in the optimization, and the new pumps are not anymore the like-for-like replacement, same with the boiler, but they are again sized towards the system which they had been operating for the last 5 years within the optimizations, which is also smaller pumps being installed. Different types of efficiencies, to quickly go through it, as I showed you previously, the condensing boiler, the efficiency, how it can be increased, and in the like-for-like replacement, why is there no increase in efficiency? They just invested in new condensing boilers. Again, if you don't tackle your return temperature and delta T problem, even the newer technologies will have a poor efficiency. In terms of CHP, for those that are interested in it, the software calculates operating time, the amount of start-stops, which it did during the year, the average continuous operating time, and of course the produced electricity. Heat pump, for those heat pumps, we see here the seasonal COP being calculated, and why are we able to provide an actual seasonal COP compared to typically the M&E consultant will use the seasonal COP which is provided by the manufacturer, and it's like buying a car. on paper it will consume a lot less. And therefore, it's important to not just use the heat pump manufacturer seasonal COP, but to actually calculate it. And because the software runs dynamic simulations on a 30-second step basis, every 30 seconds the model is looking at what's in that moment in time the evaporator temperature, what's the condenser temperature, and what's the actual COP, and that for a full year. And that's how you get an actual seasonal COP. And here we see great seasonal COPs, but imagine we would have made an alternative where we didn't do any optimizations and put the heat pumps within the existing system. We will also be able to show you how poor those heat pumps will perform. And we did. Unfortunately, we have had many projects in the last year because of PSDS where a lot of heat pumps are poorly being integrated because of not optimizing the system. A lot of data, consumption data in this area in terms of kilowatt hours, how the energy savings look like in kilowatt hours. But as a building owner, you're probably more interested in the KPI of the actual annual energy cost savings. Here we see like-for-like replacement, 12%. Hydraulically optimizing, this is what we call quick wins. Already 35% on energy cost savings is being achieved, so 3 times more, obviously. Integration of heat pumps, we can see how that performed, and of course CHP 60%. Why? Because it produces electricity. Now, carbon emission factors becoming more and more important. If you look at, for example, that 150 kilowatt air source heat pump already reduces 50% of that carbon footprint. Now we could, for example, run within the software a sensitivity analysis on different sizes of heat pumps to basically show where the most optimal heat pump size is compared to your KPI. So what's important is whatever your driver is or which ambitions you would have, we are able to show you and make you a roadmap towards those ambitions. The last KPI, which is important, is the investment analysis. Here is again taking into account those different material costs, installation costs, total cost of investments, the annual energy cost savings, and then we see here the net present values and the paybacks. Hydraulically optimizing, payback less than 3 years. For example, for this heat pump, the small heat pump unit, already a payback less than 4 years. And that makes the last KPI visible. Which investment costs do you need to make to achieve the energy cost savings and carbon emissions that you want to achieve?